Welcome back to Under the Hood. I'm Chris Gioran, Chief Architect at Neo4j. Through this series, we will dive deeply into many interesting topics, but we need to start with the fundamentals. Neo4j is a graph database, so let's start there. What does it mean to use graphs to store data, and how is this different from every other database? Let's start with the problem we're trying to solve. Both transactional processing systems and analytics pipelines have to do some modeling of the data they have to work with. Broadly speaking, application programmers will have to model some aspect of the real world, create entities out of it, and manipulate them with a programming language. Similarly, data scientists and engineers have an existing data set that they have to transform in some way to make it more suitable for large-scale analytics work. In both cases, we are after some sort of structure upon which we can model our data so we can make sense of it, transform them, and pass them around. We want to create entities that model real-world concepts, create relationships between them, put them in collections, perform business logic, or execute analytics on them, and eventually store them in a database. Modern programming languages are very flexible and allow a lot of freedom in choosing the data model we want to implement. Objects, references, and collections are examples of building blocks that allow us to represent complex domains, aided by the fact that the data will reside exclusively in memory, and therefore connections between them are always present and easy to traverse. However, for reasons we will discuss in the next video, databases will generally make use of permanent storage, which is significantly slower than main memory. To offset that, a database will generally have more rigid requirements than a programming language when it comes to how data is put together to form entities, collections, and other structures. These restrictions form the data model. One example of a data model is the relational model, which assumes entities are made up of a fixed number of fields that make up rows, which in turn make tables. Another is the document model, in which the basic building block is a collection of attributes. We also have graph databases, which explicitly model both entities and the connections between them. Given that a database is both a data source and a data sink for your application, the data model it uses naturally affects your application's design and performance, scalability, integrations, and more. The communication between applications and databases is a common point of friction. In general, you will need to translate your application domain into the data model of the database using the query language of the DBMS, which becomes more complicated as the difference between the way the application and the database treat data grows. If you have experience developing an object-oriented application with a relational database, you know the problems that appear when you try to use SQL to store and retrieve objects in a natural way. This object-relational mismatch is one of the reasons why the graph data model is much better suited for modern application development. Graph databases explicitly manage the connections between entities exactly as they are modeled in your application. And Cypher, Neo4j's query language, treats relationships as always being materialized, just like your application does. In fact, the graph data model is the closest you can get to a generic data model that maps naturally to any application, regardless of programming language, and can still function as a reliable database backend. At this point, it is important to draw a distinction between data model and schema. A specific DBMS has a data model as a core attribute and always treats data according to that data model. Schema, on the other hand, is a set of constraints put on top of a specific instance of that data model and restricts the values that can be stored. So things like uniqueness constraints, foreign key constraints, table column names, These are schema structures that are created on top of the data model. To further complicate things, the term schema itself may mean two subtly different things. Logical schema is the actual set of values stored in the database. If, for example, you store product with a price attribute in your database, then an entity called product with a price attribute is part of your schema. You don't necessarily need an explicit rule to enforce the existence of that entity, but that entity is still part of your logical schema. However, some systems require a formal set of rules that define what values are allowed to be stored in the database. These rules are also known as schema, or rule schema, to distinguish it from the logical schema. In the product example, you may be working on a relational database, which requires the user to define the existence of a table called product with a column named price. Both concepts are referred to as schema, and while all databases, by definition, have a logical schema, not all require a rule schema. In this video, we introduced the concept of data models, talked about its implications, and we saw a first example where graph databases can offer a simple solution to complex problems like application database model mismatch. This is a small example of what will become a larger theme in these videos. Modern databases must transform the complexity of data into knowledge and not just be an inert collection of facts. We will spend a large part of the series exploring this idea and its implications, but in the next video, we will talk about how Neo4j uses the graph data model to implement a highly performant, reliable, generic database that can be used as a system of record for a whole range of applications.